Also, the gas front is at the edge of the cool can make lift the convection above the level of free convection. Lastly, there will be enhanced surface flux within the cold pool by this Q and T deficit, especially at the location of the gas front where there's a large density current. Our motivation is to investigate how surface energy partitioning affects the convective organization in real case experiments using a cloud resolving model. We also want to test hypothesized cold pool effects on convective organization. Lastly, we want to explore why some observed MCSs can develop and last into nighttime. Next. We will use the WRF model. The horizontal resolution is 3 kilometers, and the land model is CLM4. We will perturb the soil moisture to vary the surface energy partitioning. A total of 14 MCS are simulated, with 9 in negative feedback regime and 5 in positive feedback regimes. And the 2006 August 10 MCS case is analyzed in detail. We will use Entraining plume model to discuss the relationship between the entrainment and the convective organization. For the observation, we will use EBER and ECOR to get the surface heat flux and the surface wind speed. We will also use the MET 1 minute wind data because the EBER and ECOR use the 30 minutes average data. Next, please. So this is the general behavior of all the experiments. The left is the dry experiment. The blue shading is the negative regime experiments, and the red shading is the positive feedbacks experiment. We can find that in this dry experiment, the wind rate is quite small overall. What is interesting is the left panel, which shows the wind rate difference between wet and the dry experiment. Before 15 local time, we can find that the larger wind rate in wet experiment than dry in positive regime, and smaller wind rate in wet than dry in negative regime. This is consistent with the convective triggering and feedback relationship. However, later on, the larger wind rate always occur on a wetter surface, regardless of the feedback regimes. Next, please. We will use this 2006 August 10 case to show that. The left panel shows the dry experiment and the right panel shows the wet experiment. In the top left, we can see many small scale cold pools in this blue shading, which shows the vertical velocity at low levels. And the deep convection, which is the black contours, is either at the center of the cold pool or at the edge of the cladding gas fronts. You can find the land type positive and negative vertical velocity perturbations. This is the turbulent horizontal rows created by the enhanced sensible heating. What's interesting here is that convection is triggered earlier in dry experiment. However, it's better organized in wet later on, as you can see from the bottom right. Next, please. The moist static energy can see the difference. The upper panels are the PDF of the dry experiments. The lower panels are PDF of wet experiment. Y-axis shows the height, and the x-axis is the MSE. We can see that there's much larger PBL MSE in this wet experiment in the bottom compared to the dry. This is mainly because of the much shallower PBL height in wet due to the lack of turbulence. The larger MSE in wet is also partly due to the reduced upward long wave radiation and reduced downward ground heat flux by this cooler surface in the wet experiment. As a result, the cape in wet is much larger than dry. Next. We believe that the Entraining plume model can at least partly explain those differences. We assume that the moist static energy is only affected by the entraining environmental moist static energy, and we assume that the increment rate doesn't change. If we have a group of increment rate, we will see a group of magenta lines as shown in this subplot. And we can get the increment rate by finding the best fit increment, best fitted line. So compared to the wet, the dry experiment has a much lower increment rate, suggesting that the colliding corpus help the triggering convection in the early stage. Also, if we look at the bottom right panels, we can find that with time, the increment rate decrease in wet in the later stage, confirming that the wider corpus and the less increment rate. Next, please. Next, please. We don't have time for this one. Okay, till now we already discussed the importance of the corpus on this early stage in the dry case and the later stage in the wet case. How about if there's no corpus? Next, please. So we clear the corpus by switching off evaporation below 2 kilometers height. Surprisingly, we found that the gas fronts still exist, except that the horizontal propagation is weaker. And more surprisingly, we found the convective organization is even slightly better than with the corpus. If we look at the bottom right, this black contour shows very organized convection. And next, please. Why is that? First, we look at the buoyancy in this in the left panels. With the corpus, there's strong negative buoyancy, and however, such strong corpus does not indicate that the gas front convection is stronger. When we take the vertical cross section in these magenta lines, we can find in the red panels that the large density current in this yellow shading will create a very slantwise updraft in these red contours. However, if without corpus, that gas front can be quite upright. Actually, this effect exists in the well-known RKW theory of scalars, but not in the current corpus parameterizations, where the gas front lifting power is only proportional to this integrated negative buoyancy. Next, please.
So I think you have about 2 minutes left.
Okay, thank you. Lastly, I want to talk about the surface latent heat flux in this shading. And the red contour represents the gas front, and the black contours represent the rain rate. What is interesting here is that in the wet experiment, the large latent heat flux in this yellow shading occurs at the location of the gas front instead of the large rain rate. This means that the enhanced latent heat flux is not only just a recycling of the precipitation, it actually could help the newly triggered convections. Next, please. In fact, we also see that enhanced latent heat flux in the observation. In this E22 is a forest site where there's a large water heat content. When the gas front passes by, there's a spike of latent heat flux, and as well as the increase of the wind speed. If we look at the 1 minute data, we also found this consistent result in the model. Next, please. Okay, to sum up, the wet soil can lead to better organized convection than dry, constituting a positive rainfall heat feedback, despite earlier triggering over dry. The enhanced surface latent heat flux along gas fronts was found in both models and observations that indicates interactions between land surface and convection. The corpus can diminish or contribute to the feedback. Their effects vary with convective life cycle stage and are not captured in parameterizations. Specifically, the slantwise gas front updraft should be considered to counter the effect of negative buoyancy, which is the only important feature in current corpus parameterizations. Perhaps the dynamical effect, such as the land shear interaction, should be more illustrated. Next, please. Thank you.
Okay, thank you very much. You got done in the allocated time. I think though, because especially, oops.
Larry?
Yes, my timer started going off.
Oh, okay.
I think given that we got a little bit of a late start, it's probably best if we just do questions in the Slack channel. So if you have questions for Yaya, I would encourage you to put them there. That way they're captured. And we'll move on to the next talk.
Our next speaker is Koichi Sakaguchi from PNL. Koichi?
Yeah, thanks for the introduction and the opportunity to share my work. Can you hear me well?
Yes.
Okay. So my work is about influence of soil moisture heterogeneity on the boundary layer dynamics and cloud, convective clouds over the SGP site in a warm day in summer. This figure in this title slide illustrates how in our WRF idealized simulations, how the vertical velocity in the boundary layer responds to the soil moisture gradient, particularly if the gradient is like in showing pretty strong. But our main interest is the spatial scale of those circulation in the boundary layer and how it relates to the spatial scale of the external forcing, like soil moisture in this case. Next slide, please. And quickly for the motivation, as probably most of us know, the accumulated evidence for the importance of area coupling of SGP site is increasing. I'm showing another study. It's, they already mentioned in previous talk, but this Welty and Zen also find strong relationship between soil moisture anomaly and the accumulated precipitation of SGP site when the data is stratified based on the large scale dynamics or moisture convergence. However, such a relationship is very difficult to model or simulate. One obvious reason is because so many processes are involved. And like in this Darmeyer et al. 2018, nicely illustrate how errors in one common component or one process can propagate and then could mess up whole the process chain. Unfortunately, we are our climate models even approaching convection permitting nice high resolutions, but that also means we are approaching gray zones for many processes. So it's important for us to understand the very spatial scale of each different processes and how this scale can change with different external forcing. The one example is the cloud size distribution here from our previous work, Fast et al. 2019. Simulations for the high-scale field campaign shows when the soil moisture is very smooth based on global analysis, the cloud is smaller and scattered. But when we have realistic variability, then the cloud is more organized and gets bigger. So we want to go more in detail on which the process underlying this change. Next slide, please. And quickly for our methodology, so we just ran WRF model for 12 hours on one of the high-scale case on August 13 to shallow to deep convection transition. And then to make our question tractable, we simplify the question a little bit. So there's no topography and no large-scale forcing. And we also focus on the local response to the soil moisture, meaning we are not looking at the later in the afternoon where the feedback from the atmosphere is important, like in the previous talk. For this feedback part, our colleague Jingjing Qian already studied in detail and published in 2020 paper, so please check it out. She has a poster about the cloud structure on the same case as well. And other details are given in the table, so you can check it out in my poster. And in the bottom, I'm showing the external forcing to the land used in this simulation. Only difference between the two simulations is the soil moisture initial condition. And one using variable soil moisture, you might notice the large wet area in the north. This is based on remote sensed product and maybe less reliable. So I'm not excluding this part from my analysis. Next slide, please. Okay, so the results. So when I take 2D FFT Fourier transform on the soil moisture and then average to the 1D representation, then our soil moisture forcing has a single clear peak around 20 kilometers, like you see on the upper right panel. And surface sensible heat flux respond directly to this mesoscale energy in pretty much same shape is created in variable soil moisture simulation, but also enhanced energy in the smaller scale, what we call sub-mesoscale between 8 and 1.5 kilometer as we defined. this enhancement of sub-mesoscale is actually lacking in the latent heat flux that is shown in the bottom. And this sub-mesoscale energy is associated with those local minima and maxima of the sensible heat flux at the surface, as well as a strong gradient created by introducing variable soil moisture. Next slide, please. And those local minima maxima and gradient of sensible heat flux become a sort of hot spots for the coupling. And then many variables, particularly related to the vertical momentum equation, showing very extreme values of those hot spots, including surface buoyancy. I'm showing some example on the top of the contour, and pressure gradient, and the near surface wind divergence, and other moisture fluxes, convergence and divergence as well. And as you can see in the near surface wind divergence map, those hot spots covers only small fraction of the area in the domain, only like less than 500 grid columns over 1 million grid columns. So we have to use log scale to really see the difference in the probability distribution I'm showing in the left, lower left. But still, once we see that the difference is really there, it's really the variable soil moisture extends those values quite to far sides and uniform soil moisture. Okay, can you go to the next slide? And have a spatial scale of the atmospheric response to soil moisture forcing. On the right, I'm showing the power spectrum again, and the top near surface buoyancy, and the second near surface wind speed. Here near surface between 70 meter and 300 meter above the ground. They both respond in the mesoscale and sub-mesoscale energy with this characteristic 2 to 3 kilometer peak, particularly in the buoyancy. The vertical velocity, we don't see any response in the mesoscale. Only response is this characteristic 3 kilometer-ish scale associated with the strong surface sensible heat flux gradient. And when we look at the spectrum of the cloud, just 1 hour later, so it's 11 o'clock compared to the 10 o'clock for the other spectra, we see energy in both sub-mesoscale and mesoscale are enhanced. When I look at the 10 o'clock power spectra, it's really has energy on the sub-mesoscale in both simulations. So what we can say is that the soil moisture variability, I mean, the cloud forms in the sub-mesoscale anyway, but its upscale growth is really enhanced by the soil moisture variability, which also you can see in the contour plots in the middle. Next slide, please. And then this signature of sub-mesoscale, in particular 2 to 3 kilometer signals in our simulations really consistently appear in many variables and levels within boundary layer. So this is another example. I'm showing the flux or covariance of the mixing ratio and horizontal velocity to the left, vertical velocity in the middle, and then just the mixing ratio variability itself on the right. And then you can see those really signature peak in all the panel within the boundary layer. But if you go above boundary layer top, like in the top panels, you don't see that signature at this time, again, late in the morning. And please, next slide, please.
So Koichi, you have about 2 minutes.
Okay, so maybe I can summarize and have some time to coffee as well. So I put this schematics to summarize the findings. So to the left is showing the cartoon for the uniform soil moisture case. Remember, we still have a realistic land cover. So we do have sensibility flux gradient, but they are relatively small. And then correspondingly, the cloud structure are more scattered, isolated, and smaller. When we introduce soil moisture variability in the, again, main energy in mesoscale, then sensible heat flux increases gradient and also magnitude. That induced mesoscale and sub-mesoscale horizontal circulations. We noted this mesoscale part is really hydrostatic, but sub-mesoscale is more non-hydrostatic. And this non-hydrostatic sub-mesoscale motion in vertical motion is also gets stronger with signature around 2 to 3 kilometer. That's the where we find enhanced energy is. But those are only happening at a small fraction of area like hotspots. And over those hotspots, clouds form earlier and then grows larger. And then when we look at the domain average, that creates those small fraction of hotspots does change the domain average precipitation and cloud cover and other statistics. And the future work, we have a bunch of future work. We got more cases. And also we are interested in scales of processes related to land cover and topography. Particularly for topography, we have our colleague Zhao Yan has a paper that how surface and subsurface runoff with topography can change those sensible and negative flux distribution, which can change the gradient and affect those circulations we are looking at. So that's one of our future work. And I'm interested in using observation from G1 aircraft during high scale and some other sensitivity test. And that's all I have.
Thanks, Koichi. I was asked to remind everyone that we're being recorded. So be sure to say nice things when you ask people's questions. And I think we probably should move on so that we can try to stay on schedule. I would encourage you, if you have questions for Koichi, to just put them in the Slack channel. The advantage of using Slack, of course, is that we keep a much longer record than what's in the Zoom chat. So the next is, I believe, a tag team talk between Tim Wagner and Dave Turner. I'll let you guys get started, and I'll give you a warning when you have about 2 minutes left.
All right, thanks, Larry. What we're doing here is we are demonstrating a technique to observe advection using the observations at the SGP site. And from that, how can we get at some interesting information about land surface and atmosphere interactions? Because of course, if you want to close the water vapor budget or many other things, you need to account for the advective influence and remove that from your observations so you can get at these more local scale changes that you might be interested in. So next slide, please. So this is not a technique that we have invented, but we are applying it to the SGP site. What we want to do is we're using Green's theorem from vector calculus. So think back all the way to when you were taking vector calculus, and you see it there on the left-hand side of your screen, some equation there. But the important thing to note is the right-hand side of that equation, del Q del X minus del P del Y, that looks an awful lot like the definition of vorticity or divergence or advection. So if you can use your observations to approximate the left-hand side of that equation and normalize by the area, then you'd be able to get at what the advection and these other kinematic quantities is. And so how you do this is you define a polygon with observations at the vertices. You find the average values of your key characteristics along each side of the polygon. You calculate the numerator term in that right-hand side for each side. It's direction dependent, so you got to move counterclockwise, make sure that you're being nice and orderly. Sum up the terms for all sides, divide by the area of the polygon, and there you go. You have a reasonable estimate of what the advection is for your domain there. Next slide, please. And so what we can do is we can take the profiles of temperature and water vapor from the areas located around SGP, which are also, of course, co-located with Doppler lidars. And so we can use that to get time and height resolved profiles of advection. And a couple of things may jump out at you here is, you know, the big thing that you see is that the Doppler lidars, they sometimes have limits to their vertical extent. We are working on that, working on some techniques and how we can extract out information from higher heights. But overall, I'm not showing it here. You can see it in my poster. This compares well to model assessed values of advection. And the other thing that we're going to do is we're going to look at the uncertainty of these observations. We can do that using a Monte Carlo approach because we're using the ARIO-E product and the Doppler LiDAR product produced by ARM, both of which have 1 sigma uncertainties. Basically, we can generate perturbed profiles and run these calculations a bunch of times and calculate the mean and the standard deviation. And so we see that the uncertainty for the temperature advection and the moisture advection is larger in the overnight hours. The vorticity uncertainty and the divergence uncertainty is larger during the day when we've got more turbulent motions in the the boundary layer and the uncertainty of the Doppler LiDAR profiles is larger. Next slide, please. So I think a question that may be of interest to this group is, what is the ideal spacing for these sites? Of course, we just use the ARM network that exists. We use the sites that we have, but maybe when it comes time for the southeastern US deployment or tracer or something like that, of how far apart do you want to place your sites in order to get the best observations? And the thing is, as you move your sites further and further away, your uncertainty or the impact of your instrument uncertainty goes down. Because quite simply, when your sites are close together and you've got an uncertainty in your observations of, say, 0.5 Kelvin, well, that's going to make a big difference in the advection if the sites are close, right? But as you push those sites away and the values in those sites are much different, then a 0.5 Kelvin difference isn't that big of a deal. So as your domain gets larger, your uncertainty goes down. But remember, to get at the advection value, you have to normalize by the area of your domain. And so as your domain gets larger and larger, your area gets larger, of course, and so your signal goes to 0 because you're dividing by a bigger and bigger number. And so what we did here is we used Monte Carlo sampling of the HER to determine this interplay between site location and instrument error. The top plot shows temperature advection at different heights. The bottom plot shows water vapor advection at different heights. The different lines are different times of the day. And by doing our Monte Carlo sampling and instrument uncertainty, these are what our uncertainties look like as a function of the domain size. And that dashed line that you see at about 70 kilometers is the scale height, the scale length of the existing ARM network. And we feel that the SGP network is basically in this sweet spot in which the error is pretty low, but there is still substantial and significant value to the signal. It's not so large that the signal has basically gone away to 0. So that's how we can measure advection. And I'll turn it over to Dave, who can show you what we can do now that we have it.
Next slide, please. Thanks, Tim. So we're going to use some mixing diagrams to one of the land-atmosphere coupling approaches that have been talked about. Alan Betts first pioneered it back in the 90s. Joe Santinello showed us about a decade ago its utility to evaluate models. You use the black shows you sort of the total evolution of the convective boundary layer from sunrise to sunset. And you can compute the contribution from radiative heating and advection. In this particular case, it's a green vector. The contribution from surface, sensible, and latent heat fluxes in brown. An encroachment term in blue, which is associated with the changing depth of the boundary layer. And then typically what's done is you derive entrainment then as the residual between the total evolution and the sum of those other terms. Next slide. And so what we've done is we've used an LES model, micro HH, to sort of simulate it to actually show, can this work? Traditionally with mixing diagrams, we've used 2 meter values, 2 meter temperature, 2 meter mixing ratio in gray. And you can see if you use the gray values, you're not actually going to get closure. To get closure, you needed to actually use mean PBL temperature, mean PBL water vapor mixing ratio. It also demonstrated the importance of getting encroachment. If you didn't include the encroachment term, then you weren't going to close either. Most, again, traditionally have sort of that residual term is included both entrainment and encroachment. One of the main reasons we got into this was to try to get at quantifying entrainment more regularly. It's a very hard variable to measure. Next slide, please. So what we have is with the ARM observations, with the area retrievals, we can retrieve temperature and moisture. That's on the left-hand side. From the potential temperature, you can estimate the depth of the boundary layer. And so if we use a layer from like 0.1 Zi to 0.5 Zi, you get the mean and mixed layer values of temperature and moisture. That's in the middle, in the top. You can also derive the encroachment term directly. You can see the changing depth of Zi with time, that's del Zi del T in the middle there. And then from that, the encroachment terms on the lower middle. And using Tim's advection values, you have the advection of moisture and temperature here, and then of course latent and sensible heat flux. So with basically the ARRI together with the an E-core station, you can get everything you need to do a mixing diagram. Next slide, please.
Dave, you have about 2 minutes.
Thanks, Larry. And so what I'm showing here on the right-hand side is the observed mixing diagram for this one case during LAFE. and then the LAS simulation that Tice did using the variational analysis. And there's a lot of similarity to these two diagrams. And so there's a lot of work to be done here to quantify, for example, the uncertainties and everything, propagate those uncertainties. But again, what we hope to do is a long-term analysis to get at statistics on encroachment and how it might be changing. I should note that the advection in this case is relatively small, but we've seen multiple cases where the advection is dominating the situation. And so that's where it's really important to say and be careful on what days are locally forced versus what days are sort of forced by the larger scale circulation. So last slide. So I'll just sort of end this with saying that we are really working to improve both our error analysis and improve the calculations of like encroachment so that we can ultimately come up with the uncertainty of the derived entrainment flux. We really want to use the large SGP data set to quantify and characterize how often advection is important. And ideally, let's see if we can create some separate classifications for these, dry CBLs and CBLs with shallow Q, so that we can try to do composite studies. And Qian and her team have done some of this already. And ideally, we'd like to be able to extend this framework to the Southeast US. And so that's why we really hope that maybe this group can help lend its voice to deploying some extended facilities that have profiling capabilities down there.
Hey, thanks, Dave. I think we have time for a question or two. So if anyone wants to raise their hand. I posed a question to Tim in Slack, and he's already given me an answer. So, there's a question that appeared in chat, Dave. I don't know if you can see it, from Neil LaRue. Any luck estimating the entrainment directly from the Raman and Doppler lidars?
So that can be done for sure. And so Christoph Senf is doing that directly. It's actually a combined entrainment plus encroachment is what they're driving with the Doppler lidar and the Raman lidar. Part of what we want to do here is be able to look at the impact of different land surfaces. And so like at SGP, some of the extended facilities are over pasture, some of it's over cropland. And what we'd like to be able to do is identify the days with very low advection values. So then you can do the same analysis over different land types. So that's part of it. And frankly, we don't have Raman lidars everywhere. But it has turned out to be a challenging measurement with the Raman lidar, Doppler lidar to get that entrainment encroachment term.
Okay. Thanks, Dave. Let's go ahead and move on. I think we're ready for the lightning talks.
Yes, we have 6 lightning talks for 3 minutes. Our first speaker is Tian from Pacific Northwest National Lab.
Thank you, Yunyan. Yeah, I know 3 minutes fly very fast. I will very quickly highlight some modeling results regarding irrigation impact on land atmosphere cloud interaction, including impact on water recycling, low-level jet, and MCS, based on our 3 papers recently published. In first study, we evaluate and quantify the irrigation impact on water recycling. We used a dynamic recycling model to track the source and sink of the moisture in atmosphere in our convection permitting simulations. Basically, a model can tell us where the added irrigation water goes. So irrigation induced precipitation increase not only over irrigated area, but also the downwind area. From the left side figure, we can see both precipitation and ET increase over irrigation area and the downwind area. And the QNet and the runoff may be positive and negative. So in summary, the irrigation increased the P and ET and recycling ratio, which suggests enhanced land atmosphere interaction and hydrological cycling. Second study focused on the impact on low-level jets. So when irrigation is considered in our simulation, the simulated low-level jets is more accurate when compared to a reference data set. So right side figure shows irrigation induced the change in frequency for low-level jet. We divided the low-level jet into 4 categories. From panel A is for the relatively weak low-level jet. Panel D is more strong, intense low-level jet. We can see, especially for those intense ones, the change in frequency of the low-level jet is pretty large, basically is a reduction. And because irrigation induced the surface cooling and the middle level trough can decrease the favorable condition for forming the low-level jets. So next slide is
you have about a minute, Win.
Okay, so the third study is, this one is impact on MCS and how consequently irrigation reduced model dry and warm bias. We applied Zerfan's tracking algorithm to monitoring and calculate the MCS during the simulation. So left panels A can see the observed MCS precipitation, B right side is simulated MCS precipitation in our control run without considering the irrigation. The bottom C and D is how about the increase of the MCS precipitation induced by irrigation. You can see the percentage increase pretty large, almost in average 65%. So overall, including irrigation improves the model, the spatial pattern, diurnal cycle, and propagation of the MCS. The increase was mainly associated with the increase in frequency of the MCS, not the intensity or lifetime. So the right panel figure shows the bottom, the top right panel is warming bias in most of the climate models. And the bottom one is irrigation-induced cooling. We can see the pattern and the magnitude is very similar. So we suggest because in this global model certainly didn't include in the irrigation, we suggest the irrigation alleviate the model, a long-standing model warm and dry bias over the central United States. So last slide is just a summary. I'm not going to read those details. So more detailed physical mechanism and process level analysis can be found in those 3 papers I listed, and certainly we can chat during post session if you have any questions. So hopefully I'm not exceeding the 3 minutes.
Yeah, a little bit.
Okay.
Thanks, Win. I would encourage people to stop by Win. Stop by the posters. So the next lightning talk is by Jingjing Tian from Lawrence Livermore.
Hello, everyone. This is Jingjing Tian, working with Yan from Lawrence Livermore National Laboratory. And our study tries to provide some observational evidence of the land cover effect on shallow cumulus cloud over the SGP. Next slide, please. High resolution GOES satellite brings the new capability to observe most of the shallow cumulus cloud with their full life cycles. However, in the GOES cloud mask product, shallow Q are not resolved and often falsely reported as the clear sky. In Tian et al. 2021, we generate a new shallow cumulus cloud mask using the GOES 16 reflectance with the aid of the DOE arm stereo cameras. And the figure A shows the diurnal cycles of the cloud occurrence probability, COP, over different land covers. And we found the COP over the open water are smallest. And in the late afternoon, the COPs over the CT are larger. And also the COPs over the forest are larger than those over the grass. And such result is supported by the DOE arm observations at the forest and the grass sites. Next slide, please. For example, over the forest, the larger friction velocity indicate more efficient exchange between the land and atmosphere. And the lower albedo indicate a greater fraction of the incoming solar energy to be partitioned into the surface heating. And some larger sensible heating may serve as a major lifting mechanism to the growth of the PBL. The heterogeneous heating over the forest and the grass may generate a secondary circulation and also influence the formation of the shallow Q. Some former LES study found the strongest secondary circulation can be triggered at optimal heterogeneity length scales. And in our observational study, focus on the figure B solid lines, which represent the COPs at cloud onset stage. And when the heterogeneity length scale is smaller than 9 kilometers, you may notice the COPs are much larger over the forest than over the grass, while at the larger scales, the COPs becomes very similar. There are very limited observational studies confirmed the preference on the heterogeneity length scale. And our study can show such signals, which is made because firstly, we bridged some observational gaps in detecting the diurnal cycles of the shallow Q and over a large heterogeneous land surface. And so that we can investigate the preference at a different time period. And secondly, we designed our analysis very carefully. For example, we separate low and high wind speed cases, and we also develop method to quantify the heterogeneity length scale on the complex land cover map. And for more details, feel free to come to my poster.
Thanks, Jingjing.
Our next speaker is Youtong Zheng from University of Maryland, and now he's at NOAA GPL, the JFDL. Yeah.
Thank you, Ian. So let's turn from coupling to decoupling. So in this work, we explore the physics of cloud surface decoupling using both armed observations and the large simulations. So here we have 3 goals in total. In the first goal, we want to test the hypothesis that only warm air advection can cause the unambiguous decoupling between the cloud and surface over the ocean. And by ambiguous, we mean that there's no cumulus coupling here. Okay, we got the warm air advection. The second goal here is to test the hypothesis that the clouds may last longer if they are decoupled from the sea surface. And this hypothesis is somewhat inconsistent with our conventional wisdom. Okay, people often think that if clouds are decoupled, they lose the moisture supply from the sea surface. So this will reduce the lifetime of the clouds. But we think here that the opposite may be true, and I will explain why. And the third goal here is to develop a new remote sensing and technology of classifying the different regimes of cloud surface decoupling over the land. And next slide, please. So here shows the results. For the first goal, our hypothesis is got confirmed. Okay, both the observations on the left and the idealized largest simulations on the right shows that the warm air advection can significantly stabilize the subcloud layer, which effectively suppress the cumulus convections, leading to a complete decoupling between the stratocumulus decks and the sea surfaces. And for second goal, our hypothesis is also proved. Okay, our idealized larger simulations show that the cloud decks can last longer in warm air advection conditions, the red line, than that in the cold air advection conditions, which is the blue line. And our interpretation is that when clouds are decoupled from the sea surfaces, the cloud layer is more quiet, in which conditions the clouds mix less effectively with the environmental dry air. This can increase the lifetime of the clouds. And for the third goal, we got a graduate student, Tian Su, who did an excellent job of synergetically using the radio sound, the LiDAR, and radar to monitor the temporal evolutions of the PBL height, cloud base height, and cloud top height. Okay, with this, we can classify the cloud regimes over the land into 3 categories, which is the decoupled clouds on the left, the coupled cumulus in the middle, and the coupled stratocumulus clouds on the right. Okay, with this, our next step is to take advantage of this new technique to study the physics of cloud surface decoupling over the land. Next slide, please. So all these presented works can be found here in the list of the references. If you have more questions, feel free to stop by my poster, which is in this afternoon. Thank you.
Thanks. The next lightning talk is by Zi Wang.
Okay, thanks. Okay, so you guys can hear me, right?
Mm-hmm. Yep.
Okay. So this work is a joint effort between the CU border and the ANCA. Lulin is leading the ANCA's effort. Now, we try to address is that PBL parameterization and that's a process. Now, as the left figure indicated, right, the PBL is complicated, so they have lots of confusion what we should call the PBL height. But here we're using this kind of the classical diagram is that, okay? So try to address the annual cycle of PBR. So eventually you have the daytime warm, daytime convective part. So we call the mixed layer. Then for this kind of the up part we call the PBR height. So now to supporting modeling, we try to providing the truth. So the right figure, the indicator or approach. So we try to use data to do the best we can to define this kind of boundary layer evolution. Then using lasso AES model, we're not run all AES. So use lasso data, then combining with a single column model to address different dynamics and the parameterization so issues. Next, please. Now this summarizes what our effort to try to get best reliable PBR and the mix and layer evolution and longer time scale. So what is this figure to show you now? The x-axis is local time, right? The y-axis is different, is showing your seasonal variation. Now you can get a PBR height with different way, but we try to focus on the using Raman LiDAR rather than aerosol. So we believe that can give you most reliable PBR height in general. For the mixing layer height, convective mixing layer, we use Doppler line vertical velocity measurements. There are a lot of literature use this one, but if you want to get reliable data, there are a lot of the issue you have to dealing with. Main thing is the gravity wave and the different scale of the eddies. And for ARM network, we have 5 Doppler LiDAR there. They also have different data quality. So we have algorithm to figure out all this kind of key issues. Now we can provide reliable seasonal and the diurnal variation of the mixed layer. So because this section is dealing with latent atmospheric, right? We have 5 data, so we didn't show results here. They do have significant difference in terms of the mixed layer development. So that may be a good indication of the land atmosphere interaction. So do exist within ARM data sets. So next, please. So this summarizes what we do with the model. Okay, so now Lulin and the NCAR team has this kind of the community physics package. So they have single column model. So we can drive this model with the select different PBR physics there, and also driving by lasso simulation, which has using different large scale dynamics. So in this case is that we can separate the large scale dynamics and the PBR physics in the simulation. So the right hand to show you the 4 PBR scheme we selected, and to show you that the mixed layer evolution driven by 3 large scale forcing from lasso. Now, what does this figure show you is the difference between model simulated and the observation, right? So the blue indicates underestimated, red is—
Qian, you're over your 3 minutes, so if maybe you could wrap up.
Yeah. So red is overestimated. So, but you can see this the performance and the different condition, right? So I think now what it just show you is the approach do working. Okay, so you can stop by the post afternoon. We can talk more in detail. Thanks.
We are moving to next talk from Ro Neggers, University of Cologne, Germany. Yeah.
All right, thanks, Jingjing. Well, good evening from Europe. Good to see you all here online. This is work we did to try to equip EDMF boundary layer scheme with knowledge of spatial organization. And of course, we now know that it's important also for boundary layers. If you don't, then many feedbacks are missed also with the surface. So very briefly, I'll explain things schematically here. On the right, you see a snapshot of a microgrid, like a lattice model. And we try to combine that with bubble theory. Bubbles being the smallest building block of convection, such as thermals. So what we do is we let these thermals being born on the grid, they can move around, they go through a life cycle, and they can interact. And this interaction makes that they cluster. And then these clusters represent coherent structures in the boundary layer that maybe do transport. and which are actually represented in our EDMF model as doing the mass flux. So we run an online clustering algorithm that gives you a size distribution of these coherent structures, as you can see here on the bottom left. And that is then fed to our EDMF scheme as a size distribution that it needs. As a result, the scheme becomes, gets rid of all its bulk closures, so it becomes decentralized. And that introduces many feedbacks that are actually beneficial for the boundary layer. And this boundary layer scheme then feeds back information about thermal birth rate, for example, W star. If you want to read more, there's a paper out that we have, and also you can ask me at my poster channel. Next slide, please. Okay, so one before, thanks. So what we did to try it out, if it doesn't crash, right? We ran it for some lasso cases. We implemented this scheme into Dales as an LES model, and we ran it as a single color model. That's basically what Peter Caldwell talked about in his talk about SCREAM. It's a great way to test physics. And then we, of course, can compare to the lasso bundle data, as you can see on the bottom. And you see that in terms of area fraction of condensed plumes, we get a pretty good diurnal evolution. And this day is pretty unique because it has this double growth phase, which is pretty hard to capture by boundary layer scheme. So something is going right. So what is going on the microgrid? That's the plot on the right. It's showing the size distribution of clusters that you get. And if you compare these three lines, one is early in the morning, the other one is later, and then one even more later, you can see that there's a clear scale growth of the cluster size. So that's interesting. So we're capturing some spatial awareness. If you, next slide, please. If you then compare how the scheme behaves before and after including this microgrid model, which we call BioMe, then you can see that it has an immediate impact on entrainment. So the bigger clusters that evolve in the new scheme make plumes go higher, and that changes the internal distribution of the cloud sizes. And as a result, the cumulus valve changes, and as a result, the boundary layer also behaves differently during the day. As you can see in the bottom two plots, the left shows that humidity stays longer, so it's drying out is less intense, and also it stays cooler. And this has a direct impact also on the surface. So these are really preliminary results. We're really in the early days. There's a lot of work to do. Next slide.
Really, you're at the end of your 3 minutes. So if you
want
to go ahead and wrap up, that'd be great.
Yes. So here you see what we have to do. We have to train the model. We have to evaluate. We have to understand feedbacks. We can do a lot more. Connect the microgrid to the surface, and also make it work for deep convection. Thanks.
Right. The next lightning talk is by Hongchen Chin from Lawrence Livermore.
Hello. So the warm biases of 2-meter air temperature over central US are widely seen in climate models, and some of which is due to overestimate of surface net radiation, some of which is due to underestimate of evaporative fraction or evaporative cooling. So people are wondering about the hypothesis that GCMs are missing mesoscale convective systems and associated precipitation. As a result, you have soil moisture deficit and underestimate of evaporative fraction. Eventually, you have T2N warm biases being developed. So this study aims to look into this hypothesis by through the lens of convection permitting simulations, in particular, a high-resolution warp simulation, which has been shown to have reasonable MCS signals in it in the Feng et al. 2018 paper. So if you move to the next slide, please. So the simulation uses Morris and Thompson microphysics, covering May to August of 2011. So those two warp simulations do suffer from the warm biases over central US during summertime. The Worf-Morrison simulation performs a bit better than the Worf-Thompson simulation in terms of T2N magnitude and spatial extent. And if we zoom into the ARM SGP site, we found that T2N warm biases occur throughout the diurnal cycle in both simulations, and the bias is 2.5 Kelvin for Worf-Morrison simulation and 3.2 Kelvin for the Worf-Thompson simulation. And the contribution from evaporative fraction is 1 Kelvin for the former and 2.1 Kelvin for the latter. Next slide, please. So when we look at the evolution of daily mean values of accumulated precipitation, we find that from May to late July, both simulations underestimate accumulated rainfall, and the categorical decomposition suggests that such differences are driven by rainfall from MCS. And both simulations tend to have soil moisture deficit. And comparing to Wolf-Morrison simulation, the Wolf-Thompson has less accumulated precipitation, lower evaporative fraction values, and larger warm biases near surface to 2 meter air temperature. So the take-home message is number one, that you can have a convection permitting MCS enabled simulation, which gives you more accumulated precipitation than observation does, but still have quite a bit of warm biases over central US during summertime. That's what the Wolf-Morrison is in this case. So number two, there's quite a bit of variability when you switch microphysics options. And in this particular case, the Wolf-Thompson simulation severely underestimated MCS rainfall, and thus you have much lower evaporative fraction values and larger T2 warm biases. Number three, this precipitation soil moisture evaporative fraction pathway is still very valuable to look at as the community moves towards convection permitting era. And in this exercise, about 40% of the warm biases can be explained by evaporative fraction in the Wolf-Morrison simulation, and the number is 66% for the Wolf-Thompson simulation. And that will do for me. Thanks for your attention.
Thank you, Hongcheng. Just to be noted that all the short talks, they have a poster session, and feel free to leave your questions in our Slack channel or their poster Slack channel. Now we are moving to the update session. That the first update is coming from Manuel Helbig, that he's new to this group, and he's coming from the AmeriFlex community. Manuel?
Yeah, thanks, Jingjing. And thanks for having me here. It's the first time being at an ASR meeting. So we had a workshop that was really looking at bringing the land flux community together with the atmospheric science community. And just a quick background, it goes back to some AmeriFlex meetings, and they resulted in a paper that has just been published online. So you can access the paper now at Agriculture and Forest Meteorology, which lines out a few of our ideas how we can enhance atmospheric observations at flux tower sites. And so a subgroup of us, next slide, please, decided to go ahead and have a workshop, and now it was a virtual workshop, really with a goal to enhance communication and collaboration between the atmospheric science and the surface flux community. And here on the right, you see, for example, the AmeriFlex tower network. So we're measuring surface fluxes at all of these sites across the Americas, focusing a lot on ecosystems, but also surface layer. And then we have on the left side more the atmospheric science community, looking up basically from the ground into the atmosphere. And next slide, please. What we really envisioned is to bring back together these communities with expertise more on, bit focused on the ecosystem side, together with more on the atmospheric side, because that's how we think is the best way forward to really understand that land atmosphere coupling in both directions. Next slide, please. So we got together an organizing committee from different countries, different universities, also for participation from Europe and from Mexico. And so we planned this virtual workshop for a long time. We had different invited talks, some big picture talks, instrumentation and remote sensing talks, some modeling perspective talks, some talks really focusing on water fluxes and water in the atmosphere, and also aerosols and clouds. And the idea was really to follow these talks with breakout sessions. We had 20 of them, so it was a logistical challenge to really get that done in a virtual environment. And then we addressed questions like, what are really the research questions that we could address by merging like really the surface flux measurements with the atmospheric side? What kind of measurements should we prioritize? And also one important question was, how can we bring the ecologists, biogeoscientists, and atmospheric scientists community together? And how can we enhance communication? And how can this enhance collaboration and lead to better understanding of biosphere-atmosphere interactions? Next slide, please. So just a bit of feedback from the workshop. I think it was a first start to really bring together these two communities, and I think like even some people here in the group were facilitators, and I think what we really saw that there is a need for more coordination. There is a need, but there was also a desire for more collaboration, and we started talking to each other and really understanding each other's work. And there were a few comments also that this really important to push high quality research. And a few things were like, for example, we should have more thermodynamic profiles, eddy covariance flux towers that measure flux, surface flux over decades already. And there were also lots of early career scientists that were able to participate because of the virtual format. And then we got some very good feedback on like how potentially this will lead to new collaborations, and and to know more about the other community, and also to challenge a bit the comfort zone of the participants to get into the other research areas. Next slide, please. So in terms of diversity, we had a quite diverse organizing committee. The invited talks were well distributed, but like from the feedback, the exit survey showed there was still a predominantly a man participating. Through the virtual format, we really were really happy that we had a lot of Hispanic participants. A lot of people from South America were able to attend, but also there was no Black or Native American attendees. So this is something perhaps we need to work on the outreach. In terms of the scientific background, I think we did a good job doing the outreach. So we had lots of people that have not received funding or not attended meetings from DOE or Ameriflux. And we got some really good feedback about how the virtual environment worked, with even a poster session in it. And also that really it helped people from Latin America to participate. And we're really happy that this worked out. Next slide. Just a few more follow-ups. So there will be a meeting report. We were thinking about what's the best outlet. It's really difficult to find an outlet that addresses both communities. It might end up in JGR Biogeoscience, which is obviously not very atmospheric science focused, but we hope it will be read. Then there will be AGU sessions. There are 2 boundary layer focus sessions. So one that I'm convening, which will be more on the ecosystem side and integrating boundary layer with ecosystem observations. And then there will be another land atmosphere interactions session, a bit broader. And there is a Google group that we hope can serve as a communication platform. If you want to participate, send an email to this email here. And there might be a special issue in agriculture and forest meteorology. And if you're interested in that, please reach out to Andrew Richardson, who is coordinating this. And then obviously we were already thinking about having another workshop next year. And the big question would also be, do we do it virtual, hybrid, and in person? Because obviously both has its pros and cons. Thanks.
We maybe have time for a question or two for Manuel. If anyone wants to either put something in the chat or raise your hand. So, Manuel, what was your kind of biggest surprise coming out of the workshop?
That's a good question. I guess because I was in the organizing committee, we already had like good communication with all the invited speakers. So I guess we had a bit of a head start. But yeah, I think it's just that there are so many like research questions that both communities kind of tackle, but from very different angles. And I think it would be good even if it would be only on the same location. So perhaps something like writing grants together and leveraging these flux tower sites that already exist for experiments or enhanced atmospheric observations. And I was really happy that there's a lot of excitement about that. And I hope the biggest challenge will be to how can we continue the communication and like push it forward, because I think the workshop was great, but it was only a first step.
Right. And I see Dave has his hand up. Dave, do you have a quick question?
Yeah, Manuel, you said one of the things that came out was the importance of putting thermodynamic profilers at the sites. But there was some concern going in that even adding salometers, which are relatively cheap, would be too expensive. Has there been any strategy on perhaps what subset of sites might be desirable for a thermodynamic profiling system?
So I think this is a really important core question, because it comes down to the costs and how much can a PI afford. And I always say for one of these, one Doppler LiDAR is about 3 new flux towers. So you need, if a Ameriflux PI goes for the money, you need to convince that person that you rather buy one instrument instead of having 3 new flux towers. So that's why I say potentially if there's interest from the atmospheric community to have like a proposal that would be located at these sites, it might be a way of having more instrumentation at these sites. I can say from my perspective, it's just the only way that I can get these instruments, and I'm trying to do that here in Canada, would be in a big infrastructure grant. And I hope so. It's really a PI driven incentive. It's a bit more difficult than to choose specifically a site that would be perfect for it, but it's more if a PI is interested in that work, it might, like a Doppler LiDAR might end up at the site. But I think like things like Raman LiDAR are really just outside the budget for most of the flux towers.
Okay, thanks, Manuel. Thanks, Dave. I think we probably should move on. So the next talk is an update on the LiDAR systems from Rob.
Yes, thank you. Everybody can hear me?
Yep.
Good. So yeah, I'll give a quick update on what's been going on with the Raman and Doppler LiDAR systems that we operate in ARM. Next slide, please. Just a quick review for those not familiar. We have 3 Raman LiDARs that we operate in ARM. We have one at SGP C1 site that's been operating there since the 1990s. We have the ENA site that's been there since 2015. It was previously deployed in Darwin from December 2010 until that site was decommissioned in 2015. And then the newest Raman LiDAR system is the AMF3 system that has been deployed up in Licktock, and since 2014 it is in the process of being taken apart and redeployed to the Southeast US as we speak. All of these systems were built by Sandia. They all use similar designs. They all provide measurements of water vapor, mixing ratio, temperature, and various aerosol and cloud properties. Next slide, please. As far as the Raman LiDARs are concerned, maybe the most significant piece of news, recent news, is not the greatest news, but it's something people should be aware of. What I have seen over the last 3 or so years from both the ENA LiDAR and the SGP LiDAR is a gradual deterioration in the sensitivity. So this is something that it's actually a little bit, the problem, it's the degradation is a little more of a problem at SGP than it is at ENA. So it's definitely something that we need to start addressing here probably over the next year or so. So it is time for a tune-up. We need to think about, how we're going to do that, what components need to be replaced and that sort of thing. Next slide, please. And then quickly on the Doppler LiDARs, for those, again, not familiar with the Doppler LiDARs, we have Doppler LiDARs operating at all of the fixed sites and all of the mobile sites. This includes a network of 5 systems at SGP. And these systems provide radial velocity measurements, as well as attenuated backscatter, signal to noise, and a new measurement that just became available with the newer systems is spectral width. So the current mode of operation is pretty simple, and this is something that I want to kind of emphasize with this particular group. We've been operating Doppler lidars for the past 10 years or so within ARM, and the way we range. And then we have one XR plus, which is like the XR, except the optics have been redesigned to provide better SNR. And you can see the packaging is a little different there. Next slide, please. So like I said, we have this network of 5 systems at SGP. We have system C1, E32, 37, 39, and 41. Over the last couple of years, we've seen a number of failures, and this has resulted in some significant downtime at some of the facilities. So in 2020, we actually went out and procured a 6th system for SGP, an XR plus system. And so the whole idea is the system operates as a spare. The XR Plus, however, is probably the best LiDAR system that Halo produces, so it's quite a capable spare system. So we took possession of that system last summer. Since then, it's been used in a number of different ways, both as a spare and for doing dual Doppler measurements at C1. The plan currently is to swap this system with the AMF2 Doppler LiDAR because Dan Feldman would like to see some scanning done for the SAIL campaign. So we've actually already done that swap. The AMF2 Doppler LiDAR that was operating on the polar stern is now at SGP E39. Also, this network, the SGP network, is really important for providing observational support for a big wind energy experiment coming up called Awaken that folks within this community may or may not be aware of. So there's these other systems. The NSA and the ENA systems have been remarkably stable for very long, continue to perform well. So knock on wood, I hope that they keep on operating well. The AMF1 system is functioning well, and we're getting ready to deploy that for Houston for Tracer, in Houston for Tracer. We are in the process of procuring new systems. Currently in progress this year, we have procurement for 2 XR Plus systems slated for either SGP or the new Southeast US site. And so we will repeat this again in FY22 with procurement of 2 additional XR Plus systems. Next slide, please. So other tidbits, little pieces of information about the LiDARs that folks should be aware of. There's interest right now in developing a new planetary boundary layer height, VAP. There's an ENG out on this. And the whole idea is to integrate observations from multiple platforms to obtain the best estimate ZI. Along those same lines, we've been looking at the application of machine learning to estimating ZI from the Doppler LiDAR and surface measurements. Raghu has a paper out in AMT on that. And now, of course, the device oscillometers are now routinely outputting ZI measurements. One thing I wanted to make people aware of here at this community is a little IOP that we conducted, or that was conducted in the fall of 2020 last year at SGP, where we had both the new spare system and the existing C1 Doppler LiDARs doing coordinated measurements. The C1 was just doing PPI scans the entire time, and the spare system was just staring vertically all the time. So that gave us high resolution horizontal wind measurements combined with uninterrupted high resolution vertical velocity measurements. And that ran for a couple, 3 months, I believe, from about October until January of this year. So this enabled retrieval of things like the turbulent flux profiles, and Raghu's got a nice poster out on that, and I invite you to see that if you haven't already checked it out. We are always examining methods for improving calibration of water vapor mixing ratio and temperature. So we're also looking at the use of machine learning techniques for that as well. And like I had mentioned earlier, I just want to kind of leave this with this group. to think about how we can make better use of the scanning capabilities that we have with the Doppler lidars. I don't have a firm answer for you. There's lots of degrees of freedom, lots of different ways we could operate these systems. So something to think about. And that's all I got.
Yeah, I think in the interest of time, we probably should be moving on. There are a couple of questions in the Slack channel. If you want to take a look at those, and if there's other questions for Rob, go ahead and put them there. So let's maybe move on.
Our next speaker is Dan Feldman from Berkeley Lab, talking about SAIL.
Hi, can you hear me?
Yes.
Yes.
Okay, great. Thanks for, I want to thank you, Qian and Larry, for the opportunity to present here today to provide this group with an update on the SAIL campaign. If you, the long and short of it here is that the SAIL campaign is a deployment of the AMF2 and an X-band scanning radar to the upper Colorado River Basin. We heard a little bit about that campaign, or at least the Doppler capabilities of that campaign from Rob just now, but I'd like to expand a little bit on that for those of you who may not be familiar. It's going to be starting imminently, the SAIL campaign in September of 2021, and the trailers are now, for the most part, at the site and energized, and so we're really excited for that. And the campaign is going to last the better part of 2 years, up through June of 2023. So that gives us an opportunity to build up some really interesting statistics and observe a number of processes in the atmosphere, at the land-atmosphere interface, and also at the within the surface and subsurface at the same time. The SAIL campaign is not going into an empty vessel. It's going into a heavily studied watershed. It's the focus of research activities that are led by the Watershed Function SFA, which is led out of Berkeley Lab and is a campaign that's supported by the Subsurface Biogeochemical Research Program within DOE. And so together, these co-located observations and modeling activities will achieve atmosphere through bedrock observation and modeling capabilities. And the big picture here is that we're looking to establish the minimum but sufficient condition ultimately to understand the atmosphere through bedrock processes that are needed to accurately predict the fluxes of water through mountainous watersheds. This is a really picturesque place, and so once we're sort of out of COVID entirely, I would encourage you to consider coming on by and taking a look. And because there's a lot of science activities and a lot of outdoor activities as well, and that's not to be discounted for developing collaborative science activities. So next slide, please. Yes, okay, so the big picture here is that water resources are really threatened in the Colorado Rockies. We've seen about a 10% decrease in the discharge from the Colorado River for every degree of warming in the last 100 years. And there's concern that will be decreasing even further in the future, and that there are a wide range of interacting processes that impact hydrology within the atmosphere, surface and subsurface, and they have dramatic seasonal variations. And when we're looking kind of at the big picture here, that the changes in precipitation and evapotranspiration are really thought to be dominating the historical water losses. Unfortunately, we're at a place where from an observational perspective, where the measurements, both of these quantities in complex terrain in these mid-latitude continental interior environments is highly limited, and it actually is limited so much that it challenges traditional model and observation intercomparisons. So when we have a sort of cartoon plot that we show here in this figure, showing the kind of the seasonal variations, and particularly focus on the left side of this figure, where we are seeing enhanced evapotranspiration under warming conditions, and perhaps decreased precipitation in complex terrain. We're trying to understand exactly how much of that is modeled and how much is observed. If you go to the next slide, please. A recent paper pointed out the fact that these areas are so underobserved that model products are better at forcing hydrological models than observational products. So that's kind of a wacky place to be, because it means that we have to be very careful with how we interpret new observation, new pointwise observations, and that having a comprehensive set of observations and modeling at the same time is a viable path to move forward out of this situation where we have lots of spatial heterogeneity and few observations, and some limitations of those observations that make it very difficult to move forward in advanced hydrological modeling. Next slide, please. Okay, so SAIL is, as I mentioned, the deployment of the AMF2. And I'm excited to present here today because there's been a lot of discussion within the SAIL team so far in terms of understanding the cold season, but the warm season is quite important, and something that we're looking to interface with this group to entrain the modeling and observational capability and science of interest of this group. So, I want to talk a little bit about the kind of some of the unique and relevant measurements that we're going to be making. One, we'll have a scanning X-band radar system at an elevated location. We did an extensive amount of beam blockage analysis, and there's been a lot of work with sighting to get this all kind of lined up. And so we have an X-band radar at a prominent location on Crested Butte Mountain, which is in the the center of this the area where the SAIL campaign will be located, and we'll have about 40 kilometers of coverage, which includes will include the AMF2 site. And we're also going to have 2 covariance systems that will enable estimates of evapotranspiration near the AMF2, and we are looking to have some other eddy covariance system measurements, and we've been in discussions with for example, the AmeriFlux rapid response system to try to cite that in the area. We also have an extensive amount of atmospheric profiling capabilities. We'll have regular SONs, an area instrument, a micropulse LiDAR, high spectral resolution LiDAR, a Doppler LiDAR with some interesting scanning capabilities. I encourage you to reach out to me if you want to do some research scans there. And we might even have a TBS. We're doing some test flights of that. This area, you can see on the right that there's some very interesting seasonal cycles in evapotranspiration that have been measured in a water limited, in an energy limited environment in the area, in a riparian zone. So we're looking to complement those existing measurements and to characterize that water flux. Next slide, please.
Daniel, could you maybe wrap up in another minute or so?
Yep, sounds good. Will do.
Okay,
thank you. Real quick, there's a large network, and of other observations. SAIL is nucleated, so to speak, a complementary campaign called Splash that NOAA is operating, and I will have a distributed another set of precipitation, evapotranspiration observations, and to characterize the surface and boundary layer. And we'll be able to use these to sample a number of N members simultaneously and provide additional atmospheric profiling capabilities. Next slide, please. Okay, and we're looking at really connecting the connections to the large scale through modeling. There's, I just want to point out that this location is at the bleeding edge of the North American monsoon, and it's collapsed in the monsoonal precipitation has collapsed in recent years. It'd be great to really advance the understanding of what is really causing that from the large scale to the local scale. I look forward to working with this group as much as possible to really drill down at to understand those connections. Final slide, please. Okay, please go to the ARM data discovery in just a few weeks, actually, and there's some really exciting opportunities. Please visit these websites for details. We have a bi-weekly teleconference that I encourage you to join, and I also have a poster in the next session. This is not just myself, but there's a large community of the SAIL PI team, and also a growing community of interest, and encourage you to join. So please, I'll be on the Slack, or you can post questions in the chat for me. Thanks.
Thanks, Daniel. I also encourage people to go ahead and put the questions in the chat or in the Slack. The next talk is about Tracer by Virendra from Argonne. And Virendra, I wonder if you could possibly try to keep it to 6 minutes.
I talk fast, so we've done.
Okay. Yes.
All right, so I'll try to talk fast. So my name is Virendra Ghate. I'm just giving a brief overview of the Tracer field campaign that will be starting very soon in the Houston area. And Mike Jensen from Brookhaven National Lab is the overall PI of the campaign. So he has a poster, you can contact him later on or contact myself. Next slide, please. So Tracer is funded by ARM, it's an ARM field campaign, but clearly I think it should be sort of named as Tracer Plus, because it's really NASA, NSF, and other agencies also have put in resources to understand things in the Houston area. So this is the overall map of the region, and I cannot really put the cursor, but you can see, maybe Qian can show the upper part. It shows the Houston city area where the things are, and where the cursor is, that's where the AMF is going to be located. So Tracer was supposed to happen last year, what was pushed back by a year because of COVID. And then at the same time, NASA and NSF was going to have their own field campaigns during that time. It's sort of pulling the resources. But what happened is that the Tracer got delayed by a year by DOE, and NASA decided to sort of go ahead and stick to the original timeline. So in September of a couple of months, 2021, the Tracer AQ campaign will happen. There's a bottom left, we can see the campaign there. That's funded by the NASA and the Texas Commission of Environmental Quality. And they have a G5 that's a nice HSRL on it, and then a lot of surface instrumentation to measure ozones and aerosol properties. I have that. And during the Tracer, when Tracer will begin from October of this year and run through the September of next year, so we have sort of a year of deployment, and there's going to be an intensive operational period. So IOP during the summer. So next summer will be IOP for Tracer. And during the Tracer IOP, there will be the Escape Field campaign that's funded by the NSF, so second from the bottom. And that's where the C-130 is going to be operational, that we have several aerosol and cloud probes on it. And the sort of cool component of the Escape campaign is going to be the mobile weather truck by the Stony Brook University and Brookhaven. and they're going to sort of sample plumes, the urban plume or the sea breeze and bay breeze, etc. So that's a sort of a niche campaign in that. And also the True Network IOP, there will be the NASA's NPOL radar, the S-band radar that's going to be operational to sort of observe the deep convective clouds, right? All right, so next slide. I need to hurry up, I guess. So I'm gonna show you a little bit more. This is a figure I put together from the Google Earth, and you see the main site on the top right here. So that's next to the bay, and that's at the Laporte Airport. And about 26 kilometers southwest of it, that's where the C-band radar is going to be located. That's a scanning C-band radar, so it will measure convective storms as passing by. And about 75 kilometers southwest of the main site will be ancillary site. And the ancillary site in my mind is pretty cool because that's where you have the aerosol instrumentation, and they're going to have radio sound launches and etc. in the IOP. And they also have the 2-channel microradiometer, so you can measure the column water vapor and liquid water paths. That's just pretty good. And one thing I want to note here, just from this figure, you can tell that the main site is sort of in the urban area. You see a lot of human footprint in there, while the ancillary site actually is in the sort of rural area in this case. As you can see, the contrast between the two sides in terms of aerosols, right? All right, next slide. This is the primary AMF location. It's on a showcase. That's at the Laporte Airport, and you see there's some maybe Union can show where the instrumentation are going to be located. That's where exactly right there. All the containers will be there, and since they manage land, there are two things I want to mention. Is number one is you can see is about 500 meters or so. There is no sort of big buildings, etc. I say airports are pretty flat. Maybe some buildings around, but they are all about 1 or 2 story buildings. And the other thing is this lack of terrain, right? So in terms of fetch for the eddy correlation systems or the Doppler LiDAR systems, it's kind of a nice site to look at things, especially when you go above 400 meters or so. Next slide, please. Other glacial observations, I would like to highlight that the region actually has 75 sites in the Houston metropolitan area that are managed by the Texas Commission on Environmental Quality, which is pretty cool. Some of the sites not only have aerosol measurement, but they also have MET measurements, etc. So it's pretty nice. Michael Young from the Texas Soil Observation Network was very kind. So he's going to put one soil observation system at the AMF3 site, and also other 2 in around the area where the ancillary site is. So that's just very nice. And obviously, for the AMA, we also have a standard surface and TBL characterization. So Doppler LiDARs, eddy correlation, fluxes, and clouds, etc. Right. So one more slide. And I want to just give a highlight about the boundary layer processes group for Tracer. So we have sort of a subgroup form, we have about 25 people or so, and our goal should to sort of organize process level studies, especially boundary layer related and land atmosphere related studies, maintain manage observation strategies, post campaign analysis, etc., and obviously do some modeling. It's led by myself and Katia Lame from Burkina National Lab. She's also heavily involved in the escape field campaign and understand the scan strategies for the Stony Brook mobile truck. So that's pretty nice. And right now we are sort of coordinating data products for boundary layer studies, like PBL height estimates, decay dissipation rates from the radar room profiler. So we are going to have that. And one neat thing we intend to do, which is all of its boundary layer focus, is to make quick loop plots. And that will give us or tell us a little bit more kind of an event catalog to understand days that have sea breeze, bay breeze, shallow cumulus conditions that are habit low advection, etc. Next slide. All right, and this is the last slide I have. I don't know if I have 6 minutes, but this is again all the subgroups Tracer Plus has, and you can see the relevant people that are organizing these groups. So please feel free to contact us if you would like to get involved. We are just sort of formation group of the formation phase of these things, and in a couple of months Tracer will be operational. Thank you.
Right, thanks, Virendra. You didn't talk quite fast enough, but you did well.
You finish in 6 minutes.
I tried.
Our next speaker is Changgai Kwang from Brookhaven National Lab. Changgai, we would appreciate that you can finish faster. Thank you very much.
No, thank you. Our team really wants to thank Larry and Yan for giving us an opportunity to share with you some land atmosphere centric updates on both our science-driven siting and measurement recommendations for deployment of this third ARM mobile facility to the southeastern United States. So why the southeastern United States, right? The DOE held a workshop in 2018 that identified the Southeast US as a priority region of interest because they have a lot of biogenic emissions, abundant shallow to deep convection that's locally forced, and then the strong local coupling of land surface with atmospheric processes. So we expect a 5-year deployment starting in the spring of 2023. And where we site, how we configure the site, and how we instrument it is going to be determined in part by recommendations from our site science team, right, which comprises aerosol, convection, and land atmosphere interaction topical areas. The next slide. Great. So, just don't worry about the text, just kind of focus on the process schematic. So we're really looking at not only topical science, but coupled topical science, right? Across convection in the upper third, aerosol processes in the middle third, and then land atmosphere two-way interactions in the bottom third, right? So you can kind of take a look at all the different type of coupled interfacial science questions we're looking at, particularly in how land atmosphere fluxes are going to be coupled to both aerosol and convection science questions. Next slide. Great, so this is our current timeline, right? So right now, from June until August 2021, our team is actively involved with site evaluations and visits. So our first site visit will be next week, right? All that is in hope for having a site identified in September 2021. And so at this point, right, we're still very much soliciting feedback from you, the community, on measurement priorities, corresponding science drivers, and also site configurations. Next slide. And so it was great to hear the earlier presentations regarding, especially from Rob regarding the Raman and Doppler LiDARs, because it kind of supports kind of the recommendations our team has been making to ARM, right, about configurations and measurement recommendations for these boundary facilities around the main one. So we recommended at least 3 non-collinear profiling facilities, right? And so we definitely are engaging with Dave Turner, Tyson, with Tim Wagner about ways in which we can be strategically configuring, right, our boundary facilities in order to kind of target these advective tendencies. We've also made recommendations for Raman LiDAR, high spectral resolution LiDAR, and Doppler LiDAR as well. And along with the other types of atmospheric profiling that we've recommended, we've also made a recommendation for a miniature aerosol observing system, right? So this is something that is a more portable version of what's at the main facility. Here are some kind of high-level criteria that we developed for siting. And I'm just going to run through some examples to give you a taste of where and why we are trying to site where we are. Next slide. So given our strong science drivers for convection, we want to be in an area that has representative cloud frequency and diversity. So we are working with these convective cloud climatology maps derived from GOES satellites that kind of point us to where are we seeing, higher frequencies of convection and where are we seeing kind of lower frequencies of convection. Next slide. And then, because of our science drivers and operational requirements, we obviously want to site in a place with low complexity. So this is a terrain roughness map that gives you a sense of areas that we want to avoid, which kind of areas in red, and areas we want to kind of be in, which are kind of areas in blue. Next slide. Let's skip this slide. Thanks. And then because of our strong land atmosphere science drivers, we also want to be in a representative forest site. So the upper panel gives us a sense of forest canopy cover, and the lower panel gives us a sense of forest canopy height. So we're using these types of maps to kind of point us towards, right, representative and preferred forest siting areas. Next slide. And so this is a busy map, but this is kind of an example composite exclusion map where we kind of folded in a lot of our siting requirements. So areas in green are kind of preferred based upon our criteria. And in this map, we're also shown an example, right? Hypothetical example site configurations for this AMF. Oh, so sorry. That was my timer. Of how we might be setting up a triangle configuration for boundary facilities around the AMF3. Again, this is just an example, but just to let you know, these are the kind of things our team is working on and trying to make recommendations for siting. Next slide. And these are then some of the persistent considerations and questions that are kind of driving our team right now as we're trying to make recommendations for preferred sites. So one consideration being, how do we balance all the disparate observational scales related to our measurement assets, right? Between flux towers and our extended measurement network. And the second consideration being, given all the heterogeneity in the Southeast United States, how do we properly capture that heterogeneity? Thanks.
Thank you. Thank you, Changgai. So maybe we still have some time for the discussion, and any questions for Changgai or all the update speakers. Yeah, we have some discussion items. Can you see my screen? I kind of frozen somehow. Yeah.
Yeah, we can see it, Yunan. And I wonder if really that first question may be the most critical if given the relatively limited amount of time, just because I know there's time constraints on getting that site, that Changgai needs for developing the site plan.
Any comments that you can raise your hand through the reaction button? Okay, finally. Dave?
Yeah, I would just say that, one of the things that we have recommended is that we have at least a triangle type facility with boundary layer profilers on the order of about 50 kilometers from the AMF location. Two reasons. One is the advection part that Tim Wagner talked about, but the second one is if you have microwave radiometers and ARES with Doppler lidars, but in particular, the microwave and ARES give you a better sampling of the cumulus fields and getting better LWP. And that's one thing that we've also learned at the SGP is you try to drive LWP and shallow cumulus fields from one site, you just get very, very poor statistics. 3 sites help a lot. You'd love to have more than that, but 3 seems to be a better number for sure.
Yeah, I thought that we had a discussion maybe a couple of weeks ago, also with the Army infrastructure team. Have they gave any updates on this yet? Maybe Changgai, some details on this issue?
On which particular issue?
The triangle that parallel in Southeast US and SGP that could characterize the cumulus retrieval by aerial E, and then also the advection terms that the team just talked about together with Dave.
Well, that's something that we want to target, right, as part of this proposed triangle configuration for our boundary facilities, and we certainly welcome any feedback and any guidance that could be provided, right, about how we instrument those boundary facilities, and especially their spacing too. So.
Yeah, I also have a question that in your first slides that how about the lower 1/3 about the canopy layer? That do we have a good idea about the site selection on this aspect that well connected to the AmeriFlux community?
it certainly is, right? And we are in active discussions with both members of Ameriflux and investigators that are part of NEON in trying to make sure, right, that we are finding the right types of forests and have the right types of resources, right, and potentially leverage and partner resources in order to get right at the sub-canopy, canopy, and above canopy type of measurements. So it's happening. Well, it's happening right now, those types of discussions.
Raghavendra, you raise your hand.
Right, yeah. So I was just wondering, Southeast US is kind of becoming a hotspot for wildfires. How are you guys taking that into consideration while you're putting up your site recommendations?
That's a really great question. In some ways, the impacts of wildfires are something that we just can't avoid due to the large number of ag fires and burns that happen, right, that are just on private land. But to the extent that we can, right, we want to partner with the Forest Service and whenever they do prescribed fires, right, so that we can understand when and where they're happening and what impacts they'll have on our measurements. And then also leverage as much as we can remote sensing to kind of get a sense of the spatial distribution and frequency of the other types of fires that, that aren't, necessarily right scheduled or provided to the larger community. But we are very much interested in like the atmospheric impacts of those wildfires as well as their land surface impacts as well.
Yeah, there's a question in the chat by Margaret. When you refer to tower sites, would those be eddy flux tower sites? And I think Sean Sherbin already answered this. Do you want to go online, answer this?
Yeah, no, that was my question. So Sean answered it.
Okay.
Oh, great.
Thank you.
Yeah, so John Guy, one question I have is, when the SGP was laid out, there was a goal of getting surface flux measurements over a range of different land use types. I wasn't sure if you and your team are thinking of a similar strategy here, or if the strategy is more to keep those satellite sites over land use land cover that's similar to the central site.
Yeah, so that is something we are considering right now, right? Because so right now we definitely want to be looking at, right? Like, so if we want to be looking at representative areas in the Southeast US, then we need to be looking both in forest land cover types and ag land cover types too, because that's just what's in the Southeast US. So those considerations, right? We are using those, right, to kind of drive some of our boundary facility siting considerations. Absolutely.
Okay. Yeah, I could imagine different science questions where either approach would be better.
You definitely got it. The challenge is real. The challenge is definitely real.
Margaret, you raised your hand.
I did want to just add one more announcement to the question about the Flex Met towers and how they could be helpful in SUS or other campaigns. And that is that DOE is giving funding to the Ameriflux Management Project to build 2 instrument packages, full FlexMet packages, that with the priority to be loaned to ARM campaigns so that we can make sure that the ARM campaigns have sufficient flux measurements for their science. It doesn't at this point include a tower. So if you needed a new tall tower at the scale of a SUS forest, that's another expense. Fortunately, ARM's really good at infrastructure, so I'm hoping they can provide that. But I wanted people to know for this campaign and future campaigns that we would like and will be able to help support flux measurements to some degree. And that's thanks to DOE.
Yeah, so Margaret, who should we contact then for this extra deployment?
That would be myself or Sebastian Barode, and I'll put that in the chat.
Thank you.
Thanks.
And Sean has a question for you, Margaret. If you can maybe answer it in the chat.
Will do.
Yeah, is there any more questions to either Changgai or other upcoming field campaign PIs, especially related to boundary layer profiling? I think also Rob has a question regarding whether we can promote some use of the scanning LiDAR radar, especially the LiDAR capability, that if anybody wants to comment on that. I see one hands. Oh, Dan, yeah, please.
Hi. Yeah, I just wanted to say that you know, just to give a little bit of perspective on the sail campaign and the scanning capability of the Doppler lidar. We, you know, I polled the PI team to develop a scan strategy that you know, that kind of balances a number of different considerations, the ongoing importance of the vertical staring, but also the value of doing PPI scans to develop a WINS, you know, a VAP product like the Doppler lidar WINS product, and also you know, some other types of scans like RHIs to capture the effects of terrain on turbulence. And so and you know, I guess that's kind of where we're at, but we're also would be interested in kind of this group's perspective, especially in the you know, kind of sampling the boundary layer processes with you know, during the warm season with research scans, and that's definitely a possibility and something that we through the sail campaign be really interested in talking with any of you more about if you are interested.
Thank you, Dan. I think we have a question in the chat. Are there any measurement available to measure canopy transpiration versus soil evaporation? I think maybe this is for either Sean or Changgai.
So we are right now, if Sean doesn't want to jump in, then we are right now working with ARM on establishing, right, a set of measurements that, you know, ARM may not typically do, but the broader community may be more familiar with in making these types of transpiration measurements. So if you have kind of specific ones in mind, definitely send either me or Sean a message, and we'll make sure those are part of our discussion.
Neil Lareau has a question for Dan. Will the Doppler lidar be proximal to a slope, such as that there could be RHN scans that capture the up-down slope flow structure, likewise for clear sky radar returns?
Yes, it's about 2 kilometers in the horizontal and 1 kilometer in the vertical away from Gothic Mountain. So there's a quite large right directly to the west. There's a quite large terrain effect from that. So we'll be able to, and I requested that the regular regular as in a few minutes every hour RHI scans in that sector.
Yeah, I think we have very active chat. So there's also questions for Laura about MPL, and Christine choose MPL retrieval. Maybe we can follow up with the Slack channel for the session. Yeah. And Sean also commented on the canopy flux measurement in the chat too. Larry, it seems that we can still have a few minutes lingering around. If this group still want to continue the discussion, that will be okay too, maybe for a few minutes.
Yeah, I think we want to be generally respectful of people's time, but if there's other questions that people do want to know, I've asked ORISE to help us save the chat. So we will have that available. And I would also encourage people to move to the Slack, because that's a good way for the rest of the group to see conversations and to jump in as they have some input.
Yeah, that would be great too, that we can keep the conversation alive still through the Slack channel. Yeah. Okay, if anybody have more comments, you can raise your hand. Otherwise, we may just end the session here.
Right, and I want to thank everyone for their presentations. I know it's a challenge always with any of these events. We try to cram 12 pounds into a 10-pound sack. And I want to thank people for doing the best you could to keep us on time and leave some time for discussion. So thanks, everyone.
Thank you very much for your contribution, all the speakers. Yeah.
Thank you.
Thank you. Thanks.